So you might have heard that computers encode information in what's called binary, zeros and ones, in order to perform their computations and to work. And so I'd like to begin with a quote. There are 1-0 types of people in the world. Those that understand binary and those who don't. And I'm hoping by the end of this unit, you will be one of those who does. So what does it mean to encode information? Well, encoding information has been going on for a long time. Anytime we've had to try and communicate in alternative ways, we might have had to encode. So for example, Morse code was a very common encoding used during World War II and earlier in World War I with the telegraph. And the alphabet and the numbers that we used to communicate were encoded in a series of dits and dots, the dots and the dashes that you see on your screen. Other ways that we've encoded information in the past might be with semaphores. Those are flags people have used. You might use a signal fire, smoke signals. All sorts of information can be encoded and has been for a long time. What we're mostly concerned with is how a computer encodes information. And it encodes information using zeros and ones, also known as bits or binary digits. One bit can convey up to 2 pieces of information, a 1 or a 0, true or false, on or off, left or right. So a single bit can be used to represent 2 things, regardless of how you assign value to those 2 things, true or false, left or right, on or off. So let's try an exercise here. Raise your left hand for true and right hand for false. 8 divided by 2 equals 4. That left hand should be up. So how many pieces of information can be conveyed with 2 arms? Let's try an example. Multiple choice. The capital of New Jersey is New York, Princeton, Trenton, or Madison. If you've got both your arms up, you are correct. So let's think about that for a minute. How many pieces of information can be conveyed with 2 arms? Well, 2 arms gives us 2 bits, and each bit, each arm, can be up or down, which gives us 4 possible combinations, if you're more mathematically inclined, permutations, and therefore 4 pieces of information can be encoded with our 2 arms. In fact, every time we add a bit, we are doubling the amount of information that we can communicate. So if we have 4 bits, we can communicate 16 or encode 16 different things. Each additional bit is doubling the number of possible permutations. So I have another question for you. How many pieces of information or permutations can we communicate with one hand that consists of 5 fingers, with each of those fingers can go up or down? Well, each permutation can represent a particular item. There are 2 to the n permutations of n bits. Therefore, n bits are needed to represent 2 to the n unique items. So for example, if we've got 1 bit, we could represent 2 items. 2 bits, 4 items. 3 bits, 8 items. 4 bits, 16 items. And if we have 5 bits, we can represent 32 items. So if I can move all 5 of my fingers independently, I can, in theory, encode 32 different things. How many fingers do we need to represent the alphabet, which is 26 letters? How much information can be encoded using 2 hands of 10 fingers? Well, in each of these cases, we can use the number of bits to help us determine. So if we have 10 fingers or 10 bits, we could encode 1024 items. And you might recognize this If you've ever tried to format a hard drive or look at the amount of space you have, you might have noticed that the storage isn't in perfectly round numbers, but it is usually close to a power of 2. So all information in a computer is stored digitally. Computers store information as bits, whether it's numbers, text, graphics and images, audio, video, or program instructions. In some way, all information is digitized, broken down into pieces and represented as numbers, which are then encoded as bits. So how does this process work? Later on in this unit, we're going to look at how we convert numbers into binary digits, into bits, zeros and ones. So for now, in this section of the learning module, we're going to focus on how do we convert information into a number. So let's say we've got text, like, "Hi, Heather." How are we going to represent that digitally? Well, we encode the information by assigning each letter, each character, its own number. So as you can see, for example, capital H is assigned the value of 72, whereas lowercase h is assigned the value of 104. There's a number of different encoding schemes for text. One of the most popular is ASCII, which is the most basic one for communicating English. It has just 8 bits or 256 different possibilities. Another more robust encoding mechanism is Unicode, which is what's been used to enable us to text emojis to one another. So we've been growing the set of characters that we can communicate. Analog information, such as sound waves, is also communicated digitally as well. And how we convert that to numbers is by a process called sampling. So an analog wave, a sound wave, is continuous and really it's infinite. You can keep zooming in and looking at it from a finer and finer granularity. However, what we end up doing to digitize music is to sample this analog signal at many different times, and we measure the magnitude of the wave, and that's what ends up becoming our number that we then encode. In the next unit, we'll take a look at how we can take these numbers and then convert them into binary zeros and ones.